Welcome. In today's session, we'll dive into the problem remove invalid parentheses.
This is a fascinating problem that challenges us to manipulate strings and manage parentheses in a way that results in valid expressions. We'll explore various approaches to solve this, from brute force to more optimized methods.
Let's get started.
In this problem, remove invalid parentheses, our goal is to take a given string and remove the minimum number of invalid parentheses so that the resulting string is valid. A string is considered valid if every opening parenthesis has a corresponding closing parenthesis, and all parentheses are properly ordered. This means that no closing parenthesis can come before its matching opening parenthesis. The solution should return all possible valid strings that can be generated by making the minimal number of removals.
The input to the problem is a single string that can contain English letters, digits, spaces, and parentheses. The output is a list of strings, representing all valid results, and the order of the output doesn't matter.
This problem challenges us to explore all potential valid configurations through careful removal of invalid parentheses while ensuring we meet the criteria of minimal changes.
Let's look at an example to better understand the problem. For the input string, there are extra closing parentheses that make the string invalid. By removing one closing parenthesis, we can generate two valid results. If we remove the closing parenthesis at position 4, the resulting string is. Alternatively, if we remove the closing parenthesis at position 6, the result is. Both of these strings are valid, and since we are required to return all possible valid outputs, both are included in the result. This demonstrates how the solution must explore different possibilities and ensure all valid strings are returned. Now, consider another example where the input string is a. This string includes not only parentheses but also the character a. The parentheses in this string are still unbalanced due to extra closing parentheses.
By removing the closing parenthesis at position 5, we get the valid string a. Similarly, by removing the closing parenthesis at position 7, we get another valid string, a. Both results are valid since they meet the criteria for balanced and properly ordered parentheses while preserving all other characters in the string. It's important to note that non-parenthesis characters, like a, are not affected and remain unchanged in the output. This highlights how the solution needs to carefully identify and remove only invalid parentheses.
Finally, let's consider a simpler example where the input string is. The parentheses in this string are completely imbalanced, as the closing parenthesis appears first, followed by an opening parenthesis. To make this string valid, we need to remove both parentheses, leaving the empty string as the only valid result. Additionally, there are constraints to keep in mind when solving this problem. The input string can be as long as 10,000 characters and may contain various characters besides parentheses. The solution must handle edge cases such as strings without any parentheses, strings with nested valid parentheses, strings with only invalid parentheses, and even an empty string as input. The key is to ensure that the minimum number of removals is performed while returning all valid configurations. To start, let's consider the brute force approach for solving the problem. The idea here is to generate all possible substrings by removing one or more parentheses in every possible combination. For each substring, we then check if it's valid, meaning that all opening parentheses have corresponding closing parentheses, and they appear in the correct order. To implement this, we first generate all these substrings, check their validity using a helper function, and track the valid ones that require the fewest removals. While this method is straightforward and easy to implement, it's highly inefficient.
Generating all subsets of the string has an exponential time complexity of O2 to the power of n, and checking validity for each subset adds even more overhead. This makes the brute force approach impractical for larger inputs due to its extreme slowness, even though it's conceptually simple.
A more efficient alternative is the breadth-first search approach.
BFS systematically explores possible strings level by level, ensuring that the first valid strings we encounter involve the minimum number of removals. Starting with the input string, we generate new strings by removing one parenthesis at a time, checking each for validity.
To avoid redundant checks, we use a visited set to store strings we've already processed.
If a string is valid, it's added to the result, and we stop exploring further at the current level. This ensures that we only find valid strings with minimal removals. BFS is significantly more efficient than brute force because it prunes the search space by stopping as soon as we reach valid results. Despite this, its time complexity remains n*2 to the power of n in the worst case, as we still need to generate and verify multiple strings.
However, it strikes a good balance between efficiency and correctness for moderately large inputs. Another optimized approach to consider is depth-first search. Unlike BFS, which explores level by level, DFS dives deep into one branch of potential solutions before backtracking and exploring other branches. This is implemented using recursion to remove parentheses and generate valid strings. We can track the number of invalid parentheses to minimize removals, and we prune paths early if we know they can't lead to a valid solution. A helper function checks validity, and we use backtracking to explore all possibilities. To avoid duplicates, we maintain a set of valid strings. While DFS has the same worst-case complexity as BFS n*2 to the power of n, it can reduce the search space significantly by pruning unnecessary branches. However, one drawback is that it may explore deeper branches unnecessarily, making it less efficient than BFS in ensuring the minimum number of removals. DFS requires careful implementation to guarantee correctness while minimizing computation. After evaluating these approaches, we chose breadth-first search as our strategy. One key insight is that the validity of a string can be checked in n using a counter to track open and close parentheses. BFS stands out because it systematically explores strings level by level, ensuring that the first valid strings we find require the minimum number of removals. This eliminates the need for post-processing to filter out non-optimal solutions. Additionally, by leveraging a visited set, we avoid redundant checks and cycles, further improving efficiency. While DFS is also a valid option, BFS avoids unnecessary exploration of deep branches, making it more practical for this specific problem. Compared to brute force, BFS significantly prunes the search space and ensures correctness. The main trade-off is that BFS uses more memory due to the queue, but in practice, it's faster for finding optimal solutions. Overall, BFS provides the best balance of efficiency, correctness, and simplicity, making it the ideal choice for removing invalid parentheses. To solve this problem, we need to determine all valid strings that can be formed by removing the minimum number of invalid parentheses from a given input string. A valid string is defined as one where every opening parenthesis has a corresponding closing parenthesis, and these pairs are correctly nested. To approach this, we first analyze the input, a string containing parentheses and possibly other characters. The task is to remove just enough parentheses to make the string valid, while ensuring all resulting strings are unique. To achieve this efficiently, we use a breadth-first search, or BFS, approach. BFS is ideal here because it processes strings level by level, guaranteeing that we only consider strings with the smallest number of removals before moving to strings with more extensive changes. This ensures that we find solutions with minimal edits first, which is a key requirement of the problem. The BFS approach begins with initialization. First, we create a queue to manage the level order traversal of strings, and we start by adding the input string to this queue. Next, we use a set to track visited strings, which prevents duplicate processing and ensures efficiency by avoiding infinite loops. We also set up a flag called found to indicate whether we have identified valid strings at the current level of BFS. Alongside this, we prepare an empty list called result, which will store all valid strings once they are discovered. As we proceed with the BFS, we process strings from the queue one by one. For each string, we first check its validity using a helper function. If it is valid, we add it to the result list and set the found flag to true. If this flag is true, we skip further processing at this level, as we are only interested in the minimum number of removals. If the string is not valid, we then generate its next level substrings by removing one parenthesis at a time, ensuring that we avoid revisiting already processed strings by checking against the visited set. The process continues until we have either found valid strings or the queue is empty. At each level, we dequeue strings, check their validity, and generate new substrings if necessary. Once we identify valid strings at the current level, we stop further exploration of deeper levels, as BFS guarantees the minimal number of removals have already been applied. At the end of the traversal, we return the result list containing all the valid strings. To support this, we use a helper function called is_valid,
which verifies whether a string has balanced parentheses. This function uses a counter to track the balance of parentheses, incrementing for opening parentheses and decrementing for closing ones. If the counter ever goes negative, the string is invalid. For the string to be valid, the counter must return to 0 after processing all characters. BFS is particularly well suited for this problem because it ensures minimal removals by design, avoids redundant work through the use of the visited set, and terminates early as soon as valid strings are found, making the algorithm both efficient and effective.
To implement the algorithm, we rely on three key data structures. A queue is used for the BFS traversal, allowing us to process strings level by level. A set is employed to track visited strings, ensuring that we don't process the same string multiple times and optimizing the search process. Finally, a list is used to store the valid strings once they are identified. In terms of complexity, the time complexity is n*2 to the power of n, where n is the length of the input string. This is because, at each level of BFS, we can generate up to n substrings, and the total number of unique substrings can be as high as 2 to the power of n. The space complexity is also n*2 to the power of n, primarily due to the storage requirements for the queue and the visited set. For edge cases, we need to handle scenarios like an empty input string, which should return an empty list, or a string with no parentheses, which is automatically valid and should be returned as is.
Additionally, strings with only invalid parentheses should be processed to return valid results after the necessary removals. Let's walk through an example to see how the algorithm works. Suppose the input string is A. We start by adding the entire string to the queue. Initially, we check its validity. Since it is invalid, we generate new substrings by removing one parenthesis at each position. These substrings are then added to the queue for further processing. As BFS progresses, we continue generating and validating strings at each level, ensuring minimal removals. Eventually, we identify valid strings like A and A, which are added to the result list. These strings satisfy the criteria of having balanced parentheses while minimizing the number of edits. The final output for this input is A, demonstrating how the algorithm efficiently finds all solutions with the smallest number of removals. To solve the problem of removing invalid parentheses, we start by importing the DEEC class from the Collections module, which will help us efficiently manage our queue for the breadth-first search. Within the solution class, we define the remove invalid parentheses method that takes a string s as input. Inside this method, there's a helper function called is_valid. This function checks whether a given string has balanced parentheses by iterating through each character, adjusting a balance variable when encountering opening or closing parentheses. If the balance ever becomes negative, it means there are unmatched closing parentheses, and the string is invalid. At the end, the function ensures the balance equals 0, meaning all parentheses are matched. Next, we initialize a queue with the input string, a visited set to track already processed strings, and an empty result list to store valid strings. The found flag indicates when we've found valid strings, which allows us to stop exploring further states unnecessarily. The while loop begins processing strings from the queue, checking if the current string is valid and adding it to the result if it is. If valid strings have been found, we skip generating new states for efficiency. Otherwise, we proceed to explore possible new strings by removing one parenthesis at a time. For each character in the current string, we check if it's a parenthesis. If it's not, we skip it since removing non-parenthesis characters would be unnecessary. For parentheses, we generate a next underscore state by removing the character at the current index. We then check if this new state has already been visited. If it hasn't, we mark it as visited and add it to the queue for further exploration. This process ensures we systematically explore all possible states without revisiting the same string multiple times, which avoids redundant computations. Once the queue is empty, meaning all potential states have been processed, we return the result list containing only the valid strings. This algorithm ensures we find all valid configurations with minimal removals, leveraging breadth-first search to prioritize results with the smallest number of changes. Here, we start by defining the Java implementation for removing invalid parentheses. The first step is to create a helper function called isValid that checks whether a given string has balanced parentheses.
This function uses a variable balance to track the number of open parentheses. As we iterate through each character in the string, we increment the balance for an opening parenthesis and decrement it for a closing one. If at any point the balance becomes negative, it means there are more closing parentheses than opening ones, so the string is invalid. At the end, the balance must be 0 to ensure all opening parentheses are properly closed. Next, we initialize our breadth first search, or BFS. We use a queue to process strings level by level, a set to keep track of visited strings to avoid processing duplicates, and a list to store the valid results. We also introduce a Boolean flag found to indicate when we discover valid strings, so we can stop searching deeper levels unnecessarily. The algorithm begins by adding the input string s to the queue and marking it as visited. Then, we enter a loop to process each string from the queue one at a time. The first step inside the loop is to check if the current string is valid using the isValidHelper function. If it is, we add it to the result list and set the found flag to true. Once we find valid solutions at the current level, we skip further processing of deeper levels within the BFS since we aim to find the shortest modifications. If the current string is not valid, we generate all possible strings by removing one parenthesis at a time. This is done by iterating through the string and removing characters at each position where there's a parenthesis. We skip any characters that are not parentheses to optimize processing. For each new string generated, we check if it has been visited before. If it hasn't, we mark it as visited and add it to the queue for further exploration. This ensures that we systematically explore all possible strings while avoiding duplicate work. Finally, once the queue is empty, we return the list of valid strings that meet the criteria. To solve the problem of removing invalid parentheses, we start by initializing a few key variables. The queue helps us maintain the strings to process, and initially, it contains just the input string. We also use a visited set to track strings we've already processed, ensuring we don't revisit the same string. The result list will store valid strings, and the found flag is used to indicate when we've found at least one valid string. The first step is to dequeue the string, and check if it is valid. By iterating through the characters and adjusting a balance counter, we find that the balance goes negative, meaning the string is invalid. At this point, no valid strings have been found, and the result list remains empty. Next, we generate neighbors by removing one parenthesis at every possible position in the string. This creates new strings like, and others. We ensure no duplicates are added by checking the visited set, and we add valid new neighbors to the queue for further exploration. Then, we process the next string in the queue, which is. Checking its validity, we find that it maintains a balance of 0 throughout, making it valid. This string is added to the result list, and we update the found flag to true, signaling that we've located at least one valid result. Once we have found a valid string, there is no need to explore invalid strings further. This is because all subsequent strings generated from invalid ones will either be redundant or less optimal. At the end of this process, the final result for the input includes two valid strings, and. Now, we move on to another example to see how the algorithm handles strings with additional characters. In this second example, the input string is A. We begin by initializing the queue with just this string, and the visited set ensures we don't process duplicates. The first string dequeued is A, and we check if it's valid. The balance counter reveals that the string is invalid due to an extra closing parenthesis. To address this, we generate neighbors by removing one parenthesis at a time, creating strings like A, and more. After updating the queue and visited set, we process A, which is valid with a balance of 0. This string is added to the result list, and since we've found a valid result, we finalize our output for this example, A and A. In the final example, the input string is N, which contains no parentheses. After initializing the queue and visited set, we dequeue the string N and verify its validity. Since there are no parentheses to consider, the string is automatically valid. It is added to the result list, and the found flag is set to true. At the end of all three examples, the outputs are as follows. For the valid strings are, and for A, the valid strings are A, and for N, the output is simply N. To analyze the time complexity of this solution, we start by considering the process of generating substrings. In the worst case,
the algorithm evaluates all possible substrings by removing one parenthesis at a time. For a string of length n, this results in at most 2 to the power of n possible substrings, since each character in the string can either be included or excluded. However, by using a breadth-first search approach, substrings are generated level by level, and the process stops as soon as a valid substring is found. This means that the worst-case time complexity for substring generation is 2 to the power of n. Next, we consider the time spent validating these substrings. Each substring must be checked for validity using the is_valid function, which involves a single pass through the string and therefore takes n time. Since there are at most 2 to the power of n substrings and each validation takes n, the total time for validation is n*2 to the power of n. Now, combining these components, the overall time complexity of the solution is dominated by the combination of substring generation and validation. This results in a worst-case time complexity of n*2 to the power of n. Turning to space complexity, we start with the queue used in the BFS process. The queue stores all unique substrings generated during traversal, and in the worst case, there are 2 to the power of n substrings to store. This means the queue requires 2 to the power of n space. Additionally, the visited set, which is used to track substrings already processed, can also grow up to 2 to the power of n in size. Finally, the is_valid function, which is called during validation, uses a constant amount of additional memory for maintaining a balance counter, contributing only 1 to the overall space complexity. Another component to consider in space complexity is the storage of the results. The result list accumulates valid substrings, and in the worst case, all 2 to the power of n substrings could be valid, requiring 2 to the power of n space. When we combine these factors, the queue, the visited set, and the result storage, the overall space complexity of the algorithm becomes 2 to the power of n. Looking at the best, average, and worst case scenarios, the best case happens when the input string is already valid. Here, the algorithm terminates immediately after the initial validation, resulting in just n time and space. On average, the algorithm explores far fewer substrings than the worst-case exponential bound due to the BFS pruning, but the behavior remains exponential overall. In the worst case, all substrings need to be explored, leading to n*2 to the power of n time and 2 to the power of n space. When comparing this approach to a brute force solution, the naive method would generate all possible substrings, up to 2 to the power of n, and validate each one. While this also results in n*2 to the power of n time complexity, it lacks the optimization provided by BFS. The BFS approach, on the other hand, generates substrings level by level and stops once valid substrings are found at a specific level, avoiding unnecessary exploration. This makes the BFS approach more efficient in practice, even though the theoretical worst-case bounds remain the same. To mathematically confirm the big O complexity, we note that the number of substrings generated is bounded by the power set of the input string, which is 2 to the power of n. Each substring undergoes a linear validation process, costing n per substring. Finally, the BFS traversal processes all unique substrings, ensuring the total work remains proportional to n*2 to the power of n. Thus, both time and space complexities are consistently n*2 to the power of n and 2 to the power of n, respectively. When working on this problem, there are a few common mistakes to watch out for. First, failing to consider edge cases can be a significant issue. These include inputs like empty strings, strings without any parentheses, or strings where all parentheses are already balanced. Overlooking these scenarios can result in bugs or unexpected runtime errors, as they often reveal weaknesses in your logic. Another mistake is relying on an inefficient brute force approach, generating all possible substrings without pruning invalid or redundant candidates. This leads to exponential time complexity, which is highly inefficient. Instead, it's crucial to leverage a BFS or DFS strategy that focuses on exploring valid candidates while avoiding duplicate computations. Additionally, many solutions ignore the order of removal when dealing with parentheses, which can create invalid results. For example, removing a closing parenthesis before its corresponding opening parenthesis disrupts the balance, resulting in invalid substrings. Finally, neglecting to track duplicates is a frequent error. This happens when the same substring is generated multiple times, especially if parentheses are removed in different orders. To prevent this, using a set to store unique substrings ensures that each one is processed only once, keeping your solution efficient and correct.
An incorrect validation function is another pitfall to avoid. For example, manually counting parentheses without a proper structure like a stack can lead to inefficiencies or errors. A stack-based or counter-based approach is typically the best practice here because it allows you to quickly and accurately determine if a string is valid. From an interview perspective, this problem showcases several key patterns. It often involves combining BFS or DFS with backtracking, demonstrating your ability to prune the search space effectively. You'll also want to highlight the trade-offs between these approaches. BFS guarantees the shortest valid result, while DFS can be simpler to implement. Being able to explain why you chose one method over the other shows strong problem-solving skills. Additionally, this is an opportunity to showcase strengths like handling edge cases, optimizing performance, and writing clean, modular code, such as separating the validation function from the main logic. Finally, be prepared to discuss the time and space complexity of your solution. While BFS typically has a complexity of (n*2 to the power of n), due to the large number of substrings generated, pruning invalid options can significantly reduce this, and explaining these optimizations can leave a strong impression. This problem is also closely related to other challenges that reinforce similar concepts. For instance, LeetCode 20, valid parentheses, is a foundational problem that focuses on using a stack to validate parentheses. It's an essential building block for understanding the mechanics of balanced strings. LeetCode 22, generate parentheses, involves creating all valid combinations of parentheses, which introduces backtracking as a key technique. Then, of course, there's LeetCode 301, the problem we're discussing now, which centers on removing the minimum number of parentheses to make a string valid. Finally, LeetCode 678, valid parenthesis string, adds another layer of complexity by introducing wildcards that can act as opening, closing, or empty characters. This variation challenges you to extend your validation logic to handle more dynamic inputs. Practicing these related problems can help you build a deeper understanding of the principles behind parentheses validation and manipulation. There are several approaches to solving this problem, each with its own advantages and trade-offs. The brute force method involves generating all possible substrings and validating each one. While straightforward to implement, this approach is highly inefficient, with a time complexity of (n*2 to the power of n, making it impractical for larger inputs. A more refined approach is breadth-first search, which generates valid substrings level by level. This ensures that the shortest valid solution is found first, but the downside is that it requires more memory to store the queue. Depth-first search is another option. It uses recursion or a stack to explore substrings and can include optimizations like skipping duplicates. While it may find valid solutions faster in some cases, it does not guarantee that the shortest solution will be discovered first. Lastly, there's the greedy validation approach, which focuses on traversing the string to determine the minimum number of invalid parentheses and removing them accordingly. This can be faster for specific cases, but it's less generalizable and can be more challenging to implement correctly for all inputs. Each method has its strengths and weaknesses, so understanding the trade-offs is key to selecting the best approach for the problem at hand. Great job! To wrap up, we reviewed the remove invalid parentheses problem and explored key strategies for solving it. This problem is a great example of algorithmic thinking, particularly in the context of string manipulation. Don't forget to practice similar problems to strengthen your understanding. Thanks for watching, and I'll see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!